Welcome to From Simple Perceptron to Transformer Architecture, not a PhD-level course that will take you on a journey through the evolution of neural networks. I'm excited to guide you through this learning experience, where we'll build a deep understanding of how AI systems have evolved, from the simplest building blocks to the sophisticated language models we see today. This course is designed to give you not just theoretical knowledge, but practical skills you can apply in your research and work. Let's begin by exploring what this course has to offer. This course is structured to take you from foundational concepts all the way to modern transformer architectures. We have 9 comprehensive lectures covering the entire spectrum of neural network evolution. But this isn't just theory. We've included 4 hands-on labs where you'll implement everything you learn using Keras and TensorFlow. On the right, you can see the 4 major areas we'll master. 1. Neural network fundamentals, understanding the building blocks. 2. Convolutional networks, for spatial pattern recognition, in images. 3. Sequential models, RNNs and LSTMs for time series and language. 4. Transformer architecture, the breakthrough behind modern AI. Each topic builds on the previous one, so by the end, you'll have a complete mental model of how these systems work. Before we dive into the technical content, I want to address something important: the fear factor. Many people believe that AI and deep learning are impossibly complex, requiring years of advanced mathematics to understand. This is a misconception that holds people back. Here's the truth. The core ideas behind neural networks are surprisingly intuitive. At their heart, neural networks are built from simple operations: addition, multiplication, and basic functions repeated many times. Yes, the math can get complex when you look at all the details, but the intuition, the understanding of why things work, is accessible to anyone who takes the time to learn it properly. That's exactly what this course will give you. We won't just show you code to copy, we'll build your intuition so you truly understand what's happening inside these models. So what do you gain when you truly understand AI intuition? First, you can debug effectively. Instead of randomly changing hyperparameters hoping something works, you'll know why your model is failing and how to fix it. Second, you can choose the right architecture. You'll understand when to use a CNN versus an RNN versus a transformer, based on real understanding, not just copying what others do. Third, you can innovate confidently. When you understand the principles, you can combine concepts in new ways to solve unique problems. Fourth, you can read research papers. The latest advances in AI won't be mysterious. You'll understand and implement state-of-the-art methods. And finally, you can communicate clearly. You'll be able to explain AI to stakeholders, team members, and anyone else with confidence. As Einstein said, if you can't explain it simply, you don't understand it well enough. Our goal is for you to understand it well enough to explain it simply. Let me be specific about what you'll be able to do after completing this course. Objective 1. You'll understand the mathematical foundations of perceptrons and MLPs, not just using them, but truly understanding why they work. Objective 2. You'll be able to design and build CNNs for image recognition, understanding concepts like convolution, pooling, and feature extraction. Objective 3. You'll implement RNNs and LSTMs, and critically, understand how LSTMs solve the vanishing gradient problem that plagued early recurrent networks. Objective 4. You'll master the transformer architecture, self-attention, positional encoding, and how LLMs process information. Objective 5. You'll have practical implementation skills with Keras, not just copying code, but writing your own models from scratch. And Objective 6. You'll be able to critically evaluate which architecture to use for different tasks. This is perhaps the most valuable skill in applied AI. Let's put this course in historical perspective with this timeline. It all started in 1958 with the perceptron, a single layer that could only do linear classification. Simple, but revolutionary for its time. In 1986, backpropagation enabled multi-layer networks, the MLP. Suddenly, we could train deeper networks and solve nonlinear problems. CNNs emerged with Lynette in 1998, introducing the idea of spatial feature extraction through convolution. This was a game-changer for image processing. LSTMs came in 1997, though they became practical later, solving the problem of learning long-term dependencies in sequences through their clever gating mechanism. And then in 2017, the transformer changed everything. The attention is all you need paper introduced self-attention, enabling parallel processing of sequences and leading to GPT, BERT, and the AI revolution we're living through now. Each architecture solved limitations of its predecessors. Understanding this evolution helps you see why each design decision was made. Theory without practice is incomplete. That's why we have 4 dedicated hands-on labs. Lab 1 focuses on neural network training with Keras. You'll build and train your first MLP, learning about model compilation, callbacks, and learning rate scheduling. This establishes your foundation. Lab 2 takes you into CNNs. You'll design convolutional architectures for image classification, understanding how to structure layers, apply pooling, and visualize what the network learns. Lab 3 is particularly valuable. You'll directly compare RNN and LSTM performance on sentiment analysis. Seeing the difference firsthand teaches you more than any lecture could. On the right, you see our toolkit: Keras for high-level model building, TensorFlow as the backend, NumPy for numerical operations, and Matplotlib for visualization. All labs include starter code, but you'll write the key components yourself. That's how real learning happens. Let's talk about who this course is for and what you need to get started. On the prerequisite side, you'll need comfort with linear algebra, matrices, vectors, dot products. Nothing too advanced, but you should know what a matrix multiplication does. Calculus is important for understanding backpropagation, specifically derivatives, gradients, and the chain rule. Again, we'll build intuition, but basic familiarity helps. Probability and statistics come up in understanding loss functions and model behavior, distributions, Bayes' theorem, expectation values, and Python programming, specifically NumPy, for array operations. You don't need to be an expert, but you should be comfortable writing Python code. Who is this course for? PhD students and researchers who want deep theoretical understanding, ML engineers looking to strengthen their foundations, and advanced practitioners who want to go beyond tutorials and truly understand the mathematics behind the models. If you're in any of these categories and have the prerequisites, you're in the right place. And with that overview complete, we're ready to begin our journey. We'll start from the humble perceptron, a single artificial neuron, and build up understanding layer by layer, concept by concept, until we reach the sophisticated transformer architectures powering today's AI systems. This isn't going to be easy. We'll dive deep into the mathematics and implement everything from scratch. But I promise you, if you engage with the material and complete the labs, you'll emerge with a genuine understanding of how these systems work. Remember, the goal isn't to memorize equations or copy code. The goal is to build intuition, to develop a mental model that lets you reason about these systems, debug problems, and create new solutions. In the next lecture, we'll start with the foundations: neural networks, perceptrons, and multi-layer perceptrons. I'm excited to have you on this journey. Let's begin.